On? Good, good. All right, then thank you for the introduction, and thank you to the organizer for putting together such a nice conference, and for giving me a chance to talk about this work here. So I will be talking mostly about this paper here, which was done with my collaborators here, and in particular, Elie and Denis are here in the audience, so if you want to ask them a question, feel free to ask them. So this is going to be the outline of my talk. I will start with a review on CFTs at finite temperature, as I'm assuming that many of you might not be familiar or so familiar with this kind of setup. Then the second part will be on bootstrapping this system. So if you want, this will be the climax of the talk. And then I will show some application, in particular for holographic theories, which I hope will be interesting for a big part of this audience, and conclude with some future direction that I find interesting. So let's start with the first part. And I want to give you some motivation for studying CFTs at finite temperature. The first thing I would like to say is that temperature is unavoidable in experiments. And one interesting and important theoretical question is if you start with at a critical point at 0 temperature and you turn on the temperature, what happens along this line here? That's where the thermal CFT lives. Another interesting aspect of thermal CFTs is that in the context of holography, they are dual to ADS black holes, so it gives you a way to study those interesting gravitational geometries. Right. I mean, so I'm thinking now of a condensed matter type of thing. So if you... All right. So, like, for instance, if you have the icy model, you get to the fixed point by tuning the temperature. If you go away from the fixed point, that's not related to going to S1. Like, that's just related to changing the coefficient of the Lagrangian and the mass, and dividing the force. So, okay, maybe we can discuss that later to not go into details here, but yeah. Anyway, let's start with something simpler anyway than this, which is how to go from a CFT at 0 temperature to finite temperature. And one way to do it is, as you were mentioning, to change the geometry. So on the left, you have a CFT on a flat space here. And you can compactify the time direction. And it turns into this cylinder geometry on the right. So here you have a circle of circumference beta, which is the inverse temperature. And this scale breaks the conformal symmetry. And in this setup, you can study correlation functions. And in particular, 2-point functions will be the focus of this talk here. So let's see how this affects the kinematics. And I prepare a table that compares 0 temperature and finite temperature cases to compare, to give some intuition. So at 0 temperature, a 2-point function is kinematically fixed to take this form here. But at finite temperature, it's not constrained and is a function of 2 variables, at least not directly. Then on the side of the OPE, the radius of convergence is finite in this geometry, so the OPE does not converge everywhere. It's important. And then on the side of the CFT data, while at 0 temperature, you have the scaling dimensions and the 0 temperature 3-point function. At finite temperature, you have those new coefficients here, B's, which are related to 1-point function in the thermal background. So here you have a 1-point function. And the residual symmetry fixes those 1-point function to take this shape here. And in particular, you have 1 open coefficient pair operators. So those are the new unknowns of the system here. And one thing that I would like to emphasize is that the spectrum stays the same even when you change the geometry. That's important for our applications. So to treat this dynamical information, we will focus on two configurations. One will be the two-point function that I showed before in full generality. And one will be a simpler configuration where the two operators are aligned in the same thermal circle. So I will refer to those two configurations as normal and easy. This might not be the best way to describe them, because actually normal is not much harder than easy, and easy is not that easy, actually. So, but this will do for today, right? So if we start on the left side, you can do a block expansion of this correlator within, if you're inside the radius of convergence. So those F here, I will not enter into detail, but they are like conformal blocks at finite temperature. And the A's, they are thermal OPE coefficients, which are related to the coefficient of the table before in this way. They are product of 3-point functions at 0 temperature and 1-point function at finite temperature. So those A's will really be the goal of our Bootstrap framework. What we want is to constrain these OPE coefficients. So now on the easy side, what happens is that this expansion simplifies a lot, and you have an expansion in powers of tau over beta, where now those coefficients here, the A delta, they are linear combinations of the AO on the left. So what you lose is the spin, the resolution with the spin here, this letter J. You have only delta here, and those are degenerate. But another advantage, which is very important, is that the OPE converges everywhere here, because you're always inside the good region. So this setup, while being easier, it still captures most of the physics. So I will talk about both setups, but often it's good to start with this to explain some physics, and then go to the normal case. So now I would like to present you the Bootstrap constraint that we will use, and it's basically periodicity. So the idea is that if you have, at least for scalars, if you have two operators on the cylinder, and one operator makes a full circle, you come back to the same configuration. So this is this constraint here. But if you include parity, one nice way to see, to rewrite this equation is this one here. And to make my point, let me set beta equal 1 from now on. This will be the case for the rest of this talk. And now you can see that this really looks like a crossing equation of the type we know and love. So here you can see this as having two channels, one S channel where you want to expand around tau equals 0, and one T channel where you want to expand around the tau equal 1. And the OPE that we saw before is not periodic. So what we want to do is to use the constraint from OPE, use the constraint from periodicity to obtain strong constraints on the correlators. To give some intuition, let me conclude this section with an example of GFF. Hopefully this will make everything more concrete for everybody. So generalized free fields, they satisfy this equation of motion. And you can calculate the correlator analytically or exactly. And what I want you to see in this expression here is that this is basically a 0 temperature propagator that you shift by this m beta, and then you sum over all the possible shifts, or over all the possible images. And the reason why I insist about this method of images is that it's something that will come back throughout this talk in various ways. So it's good to have seen it in a simple example, I think. This sum cannot be performed in general, even for free theory. But if you go to the easy setup, you can perform it, and you see those Horowitz zeta function appearing. So those are nice functions. If you've never seen them, there's nothing to be afraid of. They're really nice. And the reason I show them to you is because later on in the talk, even for interacting case, they will be the building blocks of our correlators. So my hope is that later, when the Horowitz zeta comes back, you have this warm feeling inside that you're like, this was free theory, it's simple, we're happy. I hope it happens. But to try to enforce this filling to happen, let me set delta phi equal 1 and show you that those are really very simple trigonometric function, for example, this one. Right? Now, if you look at this in a plot to gain even more intuition, the pink curve here is the usual 0 temperature 2-point function with this typical decay, while the green curve is the finite temperature correlator. And the periodicity here shows up in two ways. So one is through this mirroring structure from both sides that you can see. And the other one is that here, if you go beyond 1 and go to the next images, so to say, you should see the curve repeating again and again and again. All right, I hope that this brought a little bit of intuition around the kind of system that we want to study. Let me now move to the bootstrap. And here in vague terms, the spirit will be to use the spectrum as an input. And what we would like is that if you give us a spectrum, we are able to give you back the thermal OPE coefficient. So I hope for integrability people that this stimulates your imagination and that you can come to us with your favorite theories. And let me start this section by looking at the easy case where the 2 points, the 2 operators are aligned on the same circle. So our goal here will be to derive a formula for this correlator that encodes the analytic structure that is manifestly periodic and that contains the OPE coefficient. So to do that, we start with the analytic structure, which takes this form. So here we're in the complex time plane. And if you look on the real axis, you have all those poles that corresponds to the operators always colliding once you make a circle. And they can have branch cuts that extends in this way. So once you have this structure, you can use a Cauchy's integral formula and deform the contour to obtain a dispersion relation of this type. So the correlator here is equal to this first term here, where we drop the arcs, and we pack them into the second term here. What we like about this kind of formula is that it relates the correlator to its own discontinuity, and this is often a simpler object to deal with. Another good thing about this formula is that it is periodic, and this we enforce by summing over all the possible cuts. And one final word about this is that I will not enter into details, but one can show that the arcs are actually given by a constant, which we will refer to as kappa. So now we have this nice formula here, and the only thing that is missing from the goal of the slide before is to use DOPE, to have DOPE manifestly in this formula. So to do that, we insert DOPE in this correlator and resum, and we see the Ovid zeta appearing at this point. And you know, because you've been attentive, that this is the the GFF correlator that we saw before. So now we have a super nice formula that says that any thermal correlator can be expanded into a GFF correlator up to a constant that corresponds to the arcs that we dropped. So if we think of the list of goals that I gave before, the analytic structure is inside because that was our starting point. Periodicity is inside because we summed over all the images. And DOP is now inside. The DOP coefficients are here still unfixed. So let me now revisit the GFF example and show how this formula can be applied there, and hopefully to convince you that this is a powerful tool. So this is the formula that we just derived in the previous slide. And the spectrum for GFF is given by the identity and the double twist operator, where those operators are given by those scaling dimensions here. But if you input this spectrum in the formula at the top, what you will find is that those GFF correlator, they hold 0 when this argument is negative for integer delta. So unless they have anomalous dimension. And this immediately kills the double twist spectrum from this formula. So we get our final result, which is the one that we had before, is that it's simply given by the identity from this formula, the GF correlator. And let me emphasize that the double twist operator, it's not that they are not present. They are there. If you do a block expansion of this correlator, you will find the double twist spectrum. But from this formula, only the identity is needed to reconstruct everything. So that's the lesson of this example of GFF, is that the double twist operators, they can be reconstructed from the identity. So that shows you how you need a very small part of the spectrum really to solve the problem. Later, I will show how to apply this in interacting theory. But before that, let me quickly discuss the normal case where the spatial separation is reintroduced. So in some sense, you can do exactly the same step as before. You can derive a dispersion relation. Here it's in different variables, but you can see those as conformal cross ratios. You have a kernel here, but this is known. This can be derived, and it's not very complicated. It's periodic as before, because you sum over all the possible images again. And the arcs can be shown again to be simply a constant. Now, if you insert DOP, what you arrive to is a formula of this type, where here you have a sum over images of the conformal blocks. So it's a bit less elegant than the Ovid-Zeta formulation, but in a sense, is really the same type of formula. And it satisfies the same things that we wanted to have previously. Okay, so let me move to applications and hopefully make this whole framework more concrete for everybody. I will start by a simple example, which is the ON model in the context of the epsilon expansion. So here is a review of the ON model. So you can start with this action here and take it to the fixed point. And our goal will be to bootstrap the correlator of fundamental fields. So this is this one here, which has this dimension here for the low epsilon order. So in the case of the easy setup, we use our formula, our expansion in GFF correlator. And here we simply want to input the spectrum. So at order epsilon, the spectrum, just by normal counting, can be determined to be the identity and those double twist operators. So the identity is free theory, and I'm going to look only at the interacting part, so we can throw it away for now. And then we saw before that from the double twist spectrum, nothing will contribute to this formula unless the operators acquire anomalous dimension. And in fact, one can show that only the lowest spin of this family will receive an anomalous contribution at this order, and this is the operator phi square, while the family here will not contribute at all. So this is a huge simplification. Again, they will re-emerge as OPE coefficients once you re-expand your result, but they do not contribute in this formula. So the final result for this configuration is this one, which you can write in this form here. And the only things that are left unfixed is the free theory finite temperature OPE coefficient for phi square. So that is known. And the anomalous dimension for phi square. So this is 0 temperature input for us and is also known. So at this point, you already fixed the full correlator. And you can do this also in general for the other configuration, and you get something very similar. And we checked for sanities that this matches the corresponding Feynman diagrams. So this was a simple example, but just to see how the framework works. And now I would like to show some work in progress about 4D holographic theories, where the result is actually not known. So those are new results that should be interesting. So there's been a long-standing problem on this case, which is to determine this two-point function of scalars. at strong coupling, so in the really pure holographic regime, for integer delta phi. So for instance, that includes the case of n equal 4. And you can have this kind of picture in mind. So you have your boundary theory here with the two operators. And there is a propagator that we want to determine that is made non-trivial because of the black hole background here. And the obstacles to calculate this are the following. So even if you go in the large n limit, any multi-trace operator can in principle contribute once you turn on the temperature. You can determine this really by n counting. And that's, of course, a complication. And for this case here, the spectrum is the following. So you will have the identity as always. You will have double trace operators. They are analogous to the double twist before. But now you have also multi-stress tensor operators, which you can view as the gravitons that really make this propagator a non-trivial one. And additionally to this obstacle, we have another one, which is that so you can determine the low-lying OPE coefficient for the stress tensor sector. And what you find is that they have poles for integer delta phi. So here's an example of one. You can see that here, if you set delta phi equal 2, you have a problem. And what this means is that for integer delta phi, those poles, they have to be cancelled by contributions that come from the double trace sector. So in that way, they will be made finite. But the double trace sector, so far, there has been no way of extracting these coefficients. So this was an open problem on how to recreate this correlator fully for integer delta phi. But this degeneracies, the fact that the operators mix in this way, for analytic bootstrap, this is actually quite an advantage because you will never see those poles. You will always see the combination of the OPE coefficient, and you will always be, have a simpler formulation of this problem. So to illustrate this more precisely, consider again this easy configuration. And we take our expansion into GFF correlators. So this sum now is over the operators is finite. And in fact, as we saw before, double trace or double twist do not contribute unless they have anomalous dimension, which is not the case here. So only the multi-stress tensor coefficient appear here. So if you want, we are circumventing the problem of the poles by considering only the ones which are not degenerate, and those are the ones which do not have poles. So immediately from this formula, we are getting the correlator in this limit for arbitrary delta phi integer, and this is how it looks like for the first terms. So it has quite a nice expansion as well. So there is still this kappa to fix. Hopefully we can fix it. And before I conclude on this, let me mention that the bootstrap for the other configuration is still a work in progress because here the arcs are not trivial, but I hope we are able to do it as well. But already this correlator is a new result that was not obtained before with other methods. Okay, so let me conclude on this and discuss, take the remaining minutes that I have to discuss some future directions that I find interesting. So one of them is to consider also a compact spatial geometry. So for instance, if you put the space on a sphere, this system is very interesting because it exhibits phase transition. So on the ADS side, you have a first-order phase transition between the thermal phase and a black hole phase, which correspond on the CFT side to a confinement-deconfinement transition. So it would be fantastic to apply our tools to this setup and see if we are able to detect this phase transition through the two-point functions. Then another interesting direction is to consider defect operators, for instance, Polyakov loops, which are the other parameter of the phase transition we saw before. So we have shown in a previous work that in this setup, if you consider the correlators of either bulk or defect operators, the new open coefficients here are going to be the thermal one-point function for defect operators here compared to the rest. And one clear target for studying those is to study these correlators of defect operators here, where most of what I presented will translate into a one-to-one framework there. Then it would be great to do also some numerical bootstrap for theories where the spectrum is known to a great extent. So, of course, n equal 4, and also with or without Wilson line. And what we would like to do in this case is the following. So in previous work, we studied the ON model and produced this kind of plot. So you see each curve corresponds to a different n. And this is basically the free energy as a function of epsilon. And to create this kind of plot, those are the ingredients that were needed. We needed some rules, the knowledge of the low-lying spectrum, and understanding of the asymptotics. So for large delta, some approximation that would help us do this analysis. So now with this dispersion relation framework that I presented today, this provides an analytic control of the asymptotics. So this is good news for this kind of study. The sum rules are the same, they are universal, so, and they were derived by my collaborators in the past. And the low-lying spectrum, of course, has been studied by many people present here. And the dream would be to be able to produce this kind of plot for the free energy, but as a function of the coupling here. So really probe the non-perturbative regime for the free energy. Because there are more directions that we can consider. I will not talk about them now, but just in quick words. We can do fermions, we can do other theories that are interesting, go a bit away from criticality, work for the future. So that's it on my side. Thank you for your attention. And, let me know if you have questions. Yes, it's large n, yeah. Can you what, sorry?
Could you in principle compare it to some kind of supergravity calculation?
Yeah, I guess in principle, but I think so far the way people approach this is by solving the wave equation, and that happens to be not so easy to do. So there is a solution in momentum space in terms of Nekrasov-Shatashvili partition function. But then if you want to compare to this, you have to somehow Fourier transform it to position space. So what we are trying now to do is to solve this wave equation numerically and at least have this kind of comparison in some regime.
Yeah. Julien?
Hi. Could you give some comparison to what you do and this calculation of Joe and Simon on Hagedorn temperature? How they like related, or what?
On which one? Sorry, which?
The Hagedorn temperature.
So how to? You mean how? So about this?
In the setups and what's the main difference?
So in the setup that I showed before, if you have only the finite temperature in the infinite space, you have only the black hole space, right? You don't have a phase transition. So to be able to probe this temperature, we would have to study this geometry here. I mean, I think, I don't know, many of what we do transpose to this, but I don't want to take too many risks in saying it's a bit unclear how you would probe the Hagedorn temperature from the two-point function. So I think there we have to do some conceptual understanding of what we are actually looking for in this two-point function to probe it. I don't know if that. Right. No, this is not a large N effect. It's really just the fact that if you take this expansion in GFF correlators, you always have this argument here, and it turns out that the Ovid zeta functions that I showed before, if this is integer and negative, this just goes to 0. So if you include quantum correction, at some point the anomalous dimension kick in, and then this will not be true anymore. Then you will have this kind of, let me go back to the ON model because I think that's quite telling. You will have this kind of derivative with respect to that argument. So you need to look into favorable setups at this moment.
But I didn't really quite understand. And the status is that you say you can construct this by that condition, and then it contains the full information.
Yes. So by starting with this formula here, what this really highlights is that you need less information than if you would start with the block expansion. But still the information is there. It's just that you don't need to use it as an input.
So if you re-expand then...
so if you exactly. If you re-expand this now is in conformal blocks, all these operators will have non-zero P coefficients. Yes.
Okay. Yeah, question?
I have a question about the constant kappa.
Yes.
You know it explicitly, and on what does it depend, and is it important?
Yes, so I put it a little bit under the rug today, but in general, for me at least at this moment, the best way to have control of kappa is to consider this setup, where those have a special separation, and then you have more ways to fix this kappa. So for instance, you can request that at large distance, the correlator should decay in a certain way, so have a thermal mass or whatnot. And this will help you fix the kappa, since it's a constant that is always sticking there in whatever limit you take. So in general, you look around all the consistency conditions you have and you try to fix it. And this case is the most systematic way we have to fix it. In this other configuration, you have to be a bit more artistic about.
Yeah, Julius?
Question up here.
So, I mean, you can certainly consider correction. I'm not sure. I'm not sure at this point how they will, how it will play out. But yeah, I think you should expect them. Yeah.
Hi. So you're making this expansion of the correlator into GFF correlators. So is it correct to understand this as a kind of Polyakov bootstrap?
Yeah, I guess it is.
Like Polyakov blocks?
Similarities, right.
Yeah,
right,
okay.
Arkady?
May not be a well-defined question, but suppose you're given free energy as a function of Toft coupling and temperature. If you differentiate over Toft coupling, from the general definition, it's the same as insertion of integrated action, which is integrated dilaton operator or dimension 4 operator. So is it possible then to relate expectation value of this 1-point function to what you were talking about, if you know the free energy?
Right. So this is not something we have thought of so much, because we take the opposite approach, right? We try to extract the free energy from there. Mm-hmm. But it would be interesting to try and see if there's.
You're hopeful you can extract free energy, like.
Right.
Oh, okay.
But I guess the question is, if you would have this as an input, could you? Yeah. I think we don't know at this point, but that's an interesting question.
For free energy, it's known, you can compute leading term at strong coupling, sub-leading term at strong.
Right. I mean, in some sense, so the free energy is one of those coefficients here. It is the stress tensor 1-point function, thermal 1-point function.
Anything else? Let me just ask you, why is this so perfectly universal? I mean, do you expect if you really did something like this in n equals 4 some complexity, or you do also get the same structure?
You mean by structure, you mean this?
Yeah, I mean that you can...
Yeah, this. So we didn't rely on anything to, well, on few things. We relied to write this expression, but what you can do here is like, what I'm showing you is perturbative setup where this becomes integer, but it doesn't have to be, right? You could put the spectrum non-perturbatively and study this numerically. It becomes difficult, but
it does become...
But it's a universal expression in that sense, yes.
Okay. A very quick one about this kappa. In the holographic context, it looks like a global property of your black hole solution, right? It doesn't depend on your insertion points on the boundary. We know what the global properties of these black hole solutions are. So is this, that suggests it's some scheme-dependent thing?
No, I don't think so, because this is really, it's not going to be scheme-dependent. It's really part of this correlator here, and it can be related to an OPE coefficient. So I don't think it should be, I don't think it should be scheme-dependent.
It should be a function of the thermodynamic quantities of the black hole solution, for instance. You just don't know which one.
I think so, yeah. Yeah, I don't know. I don't know if I can comment super much on this connection, but yeah.
Thanks.
Do we have more questions? Another one. Just one more. Proceed with the schedule.
Naive questions are the hardest.
Just, if I do, for example, the Matsubara summation of this, what do I get? Do I get free energy partition function, something like that?
If you take the, sorry, say again what you want to do? To take the Matsubara sum?
Summation over the Matsubara frequency.
Of what?
Of G tau.
Of this here?
Yeah, I mean...
this is already the Matsubara sum, right?
Ah, this is already...
Like the sum is already inside, so this is the resum,
Okay.
Like, so the free theory has already a Matsubara sum inside. So.
Yeah, I think what I have in mind is to do the Fourier transformation for G tau and... okay, maybe just...
Well, yes, maybe one more, but we do need to get on.
In the 4D n = 4 example, when you have those multi-stress tensor and multi-trace operators that mix,
yes,
isn't there some like logarithmic contribution that actually contributes then to the these dispersion relations that then resolves this sort of mixing?
Well, for us, we consider them as just mixing. We are agnostic about this, right? We're agnostic about what happens with the mixing, because this is the difficult part, and indeed, logarithmic contribution should be at least naively expected. That's what we would think looking at this. So instead, what we do is, because we have this formula here, we avoid this problem altogether, because the only thing we need to make this statement is the spectrum, and that we have. So when you do this, the ones that are mixed, they just don't appear, and they reemerge in this formula here.
Thank you.
That doesn't answer directly your question, but at least that's how we deal with this problem. Yeah.
Okay, let us maybe clap again for the nice talk.